Welcome to another edition of The Explainer. I'm absolutely thrilled you're here today because we're looking at something truly mind-bending. When we look around our world, it just seems infinitely complex, doesn't it? But what if I told you that literally everything you see, touch, and even breathe is written in a single universal language? Today, we're going to learn exactly how to read it. We're exploring the core concept that chemistry is, quite simply, the language of the universe.
Okay, let's dive right into this. Here's our roadmap for today's explainer. We're going to treat chemistry just like learning a brand new language. So we'll start with the alphabet at matter, meet the 4 families of elements, check out their symbols and the periodic table, and then learn how to make words with chemical compounds, the rules of spelling, and finally, chemistry in everyday life. Let's get started with the letters. Section 1, the alphabet of matter. Take a quick second to just marvel at the incredible diversity of stuff around us. Think about the ice melting in your drink, the leather of your shoes, or the air pumped inside a football. They all look, feel, and behave completely differently, right? Yet they all share a fundamental underlying structure. Which brings me to a question I want you to really think about for a second. How many basic letters does it actually take to write the entire universe? I mean, if the English language needs 26 letters to write millions of words, how many basic building blocks are required to construct everything from a microscopic cell to a massive, swirling galaxy? Well, the answer is 118. Just 118 elements. That is our entire cosmic alphabet. Scientists have found that 92 of these are found naturally right here on Earth, in our rocks, soil, water, and air. And the other 26? Well, those are made by scientists in laboratories. Literally everything in existence is just a different combination of these 118 elemental letters. It's kind of wild to think about. But before we can start spelling words with our cosmic alphabet, we need to understand what makes our letters pure. A pure substance is basically a material made up of only one kind of particle. Whether you look at a single tiny drop of pure water or an entire swimming pool of it, the composition and behavior are completely identical throughout. It hasn't been mixed with absolutely anything else. Now, within these pure substances, we've got a really crucial distinction to make. First, we have elements. These are the simplest substances made of only one kind of atom. They're your standalone letters. They just can't be broken down into anything simpler. But when 2 or more elements are chemically combined, we get compounds. So if elements are our individual letters, compounds are the words formed when these letters join hands. All right, moving into section 2, 4 families of elements. Just like human languages categorize letters into consonants and vowels, our elemental letters are divided into distinct families based on their unique personalities and properties. Let's look at the 2 biggest families. First up, we've got metals. They make up the vast majority of our 118 elements. They're the heavy lifters, usually shiny, solid, dense, and fantastic conductors of heat and electricity. You can hammer them into thin sheets, which we call being malleable, or stretch them into wires, known as being ductile. Now contrast that with nonmetals. They're the complete opposite. They are dull, brittle, have low melting points, and are very poor conductors. If you try to stretch or hammer a nonmetal, it's just going to shatter into pieces. But hey, nature loves an exception, doesn't it? Enter the metalloids. These are the absolute rule breakers. Elements like silicon or arsenic fall right in the middle, showing some properties of metals and some of nonmetals. Because of this really mixed, highly specific behavior, metalloids are absolutely crucial for modern technology. I mean, they're the reason the electronic device you're probably using right now actually works. Our 4th family is the noble gases, and they're fascinating because they are inert. They really don't like reacting with other elements. A brilliant real-world application of this is happening right now in airports in places like Chandigarh and Amritsar. They use neon, which is a noble gas, in their runway lighting. Why? Because when electricity passes through it, neon emits this incredibly bright reddish-orange glow that perfectly cuts through thick winter fog. It's safe, reliable, and literally guides planes safely to the ground. Moving right along to section 3, symbols and the table. Writing out the full names of elements every single time would be totally exhausting. Scientists needed a universal shorthand to write these cosmic letters down quickly and easily, regardless of what human language they actually spoke. We actually have 2 scientists to thank for how we visualize this today. John Dalton was the pioneer who first described atoms, but it was a scientist named Berzelius who created the clever 1- or 2-letter symbol system we still use right now. He usually took the first letter of an element's English or Latin name. For instance, oxygen is simply O, but iron is Fe, which comes from its Latin name ferrum. Pretty cool, right? And this brilliantly illustrates how all those symbols live in one perfectly organized place, the periodic table of elements. It doesn't just list the elements randomly, it organizes them perfectly by atomic number. The horizontal rows are called periods, and the vertical columns are called groups. Elements sitting in the same column usually share similar properties, making it an incredibly powerful cheat sheet for scientists. So, where are all these popular elemental letters actually hiding? Well, in the entire universe, hydrogen and helium totally dominate. In fact, hydrogen was the very first element formed right after the Big Bang. Down here on Earth's crust, oxygen and silicon are the most abundant. The air we breathe is mostly nitrogen. And inside you and me, the human body is primarily a combination of carbon, hydrogen, and oxygen. Which brings us to Section 4, Making Words, Chemical Compounds. We know our letters, so now it's time to start combining them to form words. When elements join together chemically in a fixed ratio, they create an entirely new, pure substance called a compound. Now, what's really mind-blowing here is how a compound completely sheds the identities of its parent elements. Take sodium, for example. It's a highly reactive metal, so explosive it literally has to be stored under kerosene just to keep it away from the moisture in the air. Chlorine is a highly poisonous greenish-yellow gas. But when you chemically combine these two incredibly dangerous elements, you get sodium chloride. You know it better as table salt. No way, right? Two deadly elements combine to make something totally safe, white, solid, and essential for our daily nutrition. Understanding how to manipulate these compounds allows scientists to innovate in some pretty incredible ways. What we're looking at here is shatter-resistant transparent wood. Scientists figured out how to remove a compound called lignin, which gives wood its brown color, and fill the remaining gaps with a clear, plastic-like compound. The result? An eco-friendly material that lets light pass through just like glass. That is the true power of mastering chemical compounds. Section 5. The Rules of Spelling. Just like you can't just mash random letters on a keyboard and expect a real word, you can't just mash random elements together. There are strict spelling rules in chemistry, and we represent them using chemical formulae. The ultimate rulebook for spelling these chemical words is called valency. Valency is simply the combining capacity of each element. Think of it kind of like the number of hands an element has to hold on to other elements. It dictates the exact, simple whole number ratio needed to form a stable compound. So how do we actually write a formula? Well, we use a remarkably simple trick called the crisscross method. Let's walk through the steps using water to keep it simple. Step 1. Write the symbols side by side. So H for hydrogen, O for oxygen. Step 2, write their valency, or combining capacity, right below them. Hydrogen has a capacity of 1, oxygen has 2. Step 3, crisscross them. The 2 from oxygen drops down next to the hydrogen, and the 1 from hydrogen drops next to the oxygen. And the result is H2O. A chemical formula acts as a perfectly efficient recipe. It tells us not only which elements are present, but the exact number of atoms of each. For example, the formula CO2 tells us immediately that this molecule contains exactly 1 atom of carbon and 2 atoms of oxygen. It's precise, it's universal, and it's incredibly elegant. Which brings us to our final section, chemistry in everyday life. It's super easy to think of atoms and valency as abstract textbook concepts, but they literally dictate the tangible reality you interact with every single day. Let's look at a few rapid-fire daily applications. Because we know copper is a highly ductile metal and a great conductor, we use it to wire our homes. Because we know diamond, which, by the way, is actually just pure carbon, is the hardest natural substance, we use it in industrial tools to cut glass. Because we know certain plastics are great insulators, we use them on the handles of frying pans so we don't burn our hands while cooking. The unique properties of these different elements and compounds dictate exactly how we build our world.
And that brings us to the end of our journey today. From the 11 simple letters forged in stars and laboratories to the infinite complexity of the compounds that make up our bodies and our entire world, chemistry really is the language of reality. I want to leave you with this thought. Now that you know the alphabet of the universe and we're seeing things like shatterproof transparent wood, what new words do you think science will spell next? The possibilities are quite literally infinite. Thanks for joining me on this explainer. Keep your curiosity alive, and I will see you next time.